Good morning, everyone. Very glad to be here with you today. And hello from Peter. He's in Cape Town, South Africa today, back home at a conference going on down there. So I'll be talking, kind of shifting gears a little bit to talk about the benefits of internal curing and using lightweight fine aggregate for concrete pavement overlays. This is a project that the CP Tech Center at Iowa State did back in 2018, or at least the construction was back in 2018. I was not on staff at CP Tech Center or at Iowa State at the time that this was done, but hopefully I can do a good job of doing justice to the study that they did at the time. And I actually was, just as someone who was interested in this project working in the industry, I actually was present for the construction, so I was able to use some of my own photos even in this presentation here. But we'll go through quickly, talk about reducing global warming potential and some pavement-specific items that we want to look at, and things that, internal curing may provide some benefits that are particular for this use case, in particular for concrete overlays. Brief introduction to overlays if you're not familiar with using them for pavements. We'll talk about that internal curing pilot project that was done a few years ago, and then at the end put it all together to demonstrate or to at least show the benefits that we might be able to achieve from using internal curing in concrete overlays. So with respect to global warming potential, I think, it's been a very common theme of, concrete and all types of infrastructure in recent years is that, we're recognizing the impacts of climate change, the need to reduce future CO2 emissions, and that cement is a fairly significant contributor to those emissions. And so we do want to seek to reduce embodied carbon emissions of concrete, but obviously we want to do this without compromising the quality or the performance of the infrastructure. And in fact, designing our infrastructure to be longer lasting, again, common theme, and we've already been touching on that in the session here this morning, is a good way to reduce the life cycle emissions of our infrastructure. And so again, I think in all different sectors and all different types of concrete buildings and structures, transportation infrastructure certainly, we talk a lot about embodied carbon emissions. And so we talk about, in a pavements context, if we can find ways to reduce the amount of concrete we need to use in the pavement through optimizing design, potentially use less binder in the concrete mix itself, or even have a binder that contains less Portland cement clinker, are all good ways to reduce embodied carbon emissions. But again, we do want to make sure we're thinking life cycle as well. So, from a maintenance and rehabilitation point of view, if we can build a pavement that requires less future work so that we don't have to use as many new raw materials to keep it in good condition over its entire service life, that can obviously be helpful. And then one thing that is pavement specific, if you don't work in this context very often, but can be really significant, is that pavements have quite a bit of influence over the fuel consumption by the vehicles traveling over the pavement. So the surface characteristics of a pavement itself, chiefly the roughness of the pavement and also the deflection or the amount of deflection that the pavement experiences as a traffic load travels over the pavement, those can end up having a pretty significant of influence on the amount of fuel that a vehicle needs to use to continue operating at the particular speed that it's going. So what we find is, beyond just thinking life cycle and reducing future maintenance costs and things like that, if we can keep our pavements in good condition for the long term, and particularly if we can help ensure that they remain smooth over the long term, that can end up having quite a bit of an impact on the overall life cycle global warming potential that we can measure or model or calculate for our pavement system. So it is a pretty significant area of interest right now, within the pavement community. So to talk about concrete pavement overlays, if you're not familiar, very simply, it's a maintenance, rehabilitation, preservation method, however you want to consider it, to extend the life of an existing pavement with an overlay of a new concrete surface. It can be applied to any type of concrete pavement, whether it's an existing concrete or asphalt surface. You can see here we're overlaying in this just an example picture. We've got an existing asphalt pavement. It's been profile milled, but then we're just coming in with a slip form paving machine without doing any other type of surface prep or anything like that, and paving a new concrete overlay right on top. And so again, concrete overlays have the potential for a lot of long-term benefits, both in terms of life cycle cost, but as well as when we start looking at life cycle carbon emissions. Obviously we have the ability to upgrade an existing distressed pavement, so put it into better condition, better able to allow traffic loads to travel over it without experiencing as much roughness or deflection. We're able to use equity and resources invested in the original pavement. Generally, concrete overlays generally they are not as thick as a conventional pavement because they do have some underlying pavement structure that they're able to rely on for load carrying capacity. Certainly compared to new construction, it reduces the amount of time and the amount of energy that you need for the construction process. And again, because they're not as thick as conventional pavements, we're using less raw materials. And then if you do compare concrete overlays to other types of pavement rehabilitation, whether you're talking very, very thin surface treatments or conventional thickness asphalt overlays, one of the additional benefits is that you can design concrete overlays, and they are consistently designed to achieve very long-term service life on the order of 30 or 40 years. And so again, being able to build something, one time and keep it in good condition, could have some long-term benefits as well from an environmental point of view relative to other pavement rehabilitation techniques. And now we get to curing. So, our typical conventional curing process for concrete pavements is to use a white pigmented curing compound that we apply to the surface and the sides of the slab. And obviously, again, just like bridge decks, concrete pavements are exposed to the elements. It's a very harsh environment. We're going to be placing de-icing chemicals on the concrete pavement. So anything that we can do to keep as much water in the system during hydration to promote good curing, and in particular to make sure that the surface doesn't dry out and that we don't end up with a weak surface that might be susceptible to scaling or, susceptible to future joint deterioration issues. Curing is a really critical part of the construction process for concrete pavements, and it really is critical to getting the longevity and durability that we're looking for concrete pavements. And so internal curing can obviously have a lot of benefits to all types of concrete structures, as we've been talking about this morning. But again, some of the key things that we're interested in from a pavement's point of view, in addition to just enhanced hydration and enhanced properties, the ability to reduce the moisture differentials that develop as concrete is setting, and to reduce shrinkage, those could have a number of different benefits for concrete pavements. And particularly when we start looking at concrete overlays, again, these are thinner than conventional full-depth concrete pavement slabs, usually on the order of a couple of inches, the way most projects are designed and built, at least I can certainly speak to the Midwest. And so we do have a situation here where more surface area of our concrete slab is exposed relative to the volume of concrete in the overlay system, relative to a thicker pavement. So curing is even more critical to ensure that we do get good performance out of our concrete overlays. And at least you have the potential for increased susceptibility to some of the types of performance issues that you might see if you don't get adequate curing, or if large moisture gradients do develop in the slab. In particular, what you see pictured here is warping. So if we do get a moisture gradient that develops in the concrete slab, warping can both obviously cause the shape of the slab to change, and that could increase the roughness of the pavement, both right from the beginning and increasingly over its life. It can also induce additional stresses and potentially reduce the fatigue life of the slab if you do have a significant amount of warping. And obviously, the temperature gradient plays a role in this as well, and sometimes they're lumped together, and you'll see curling and warping kind of used interchangeably. But the moisture gradient plays a significant role in that process, and that's obviously even just an addition to the potential for shrinkage cracking, especially if we're in dry conditions and the pavement isn't well cured. And again, just susceptibility to other types of surface stresses and potential for joint deterioration related issues. And so again, looking at the sets of things that we're particularly concerned at with respect to curing, that's where internal curing does jump out as being useful, not just for pavements in general, but particularly for concrete overlays, where again, because of the thinner nature of this pavement system, it might potentially play a larger role or give us a greater benefit and just reduce the probability of having these potential problems. So jumping now to the project that was built, this was on a county highway in Washington County, Iowa. This was a 6-inch thick concrete overlay. The terminology you see there, COCU, that's concrete on concrete unbonded overlay. So the existing pavement was a concrete pavement. You can actually see here, though, they're paving on asphalt because they're using an asphalt separation layer to relieve stresses, prevent reflective cracking from the joints in the underlying concrete pavement into the overlay. And the section was instrumented with temperature and moisture monitors, and they were using lightweight fine aggregate as the form of internal curing. We see the mixture proportions here. These are given in pounds per cubic yard. I do believe it was designed just like the bridge project we were just looking at in Georgia for that 7 pounds of water per 100 pounds of cement. What that ended up being was about 35% of the natural sand that was the normal fine aggregate here was replaced by the lightweight fine aggregate. So just some notes from the construction. Everything went very smoothly out on the grade. The test section here, it wasn't the entire project was not paved this way. It was a test section that was, I think, about 500 feet long. And so you have a lot of control, and we were able to instrument the control section alongside this internally cured section. The contractor, they set up a central batch plant for this project, so they were running their own plant. They didn't note any issues soaking or draining the stockpile of the lightweight fine aggregate. It was, as we mentioned here, it was soaked for 3 days and then drained for 24 hours prior to construction. Obviously, the quantities, since they were only paving for 500 feet, were fairly limited, but they didn't, perceive any major logistical issues with that. The lightweight fine aggregate was batched, assuming saturated surface dry. Overall, all the operations at the plant went well. Out on the grade, finishing crew didn't really observe any differences between the control mix and the internally cured mix. They did notice, actually, that the mix, maybe it looked a little bit wet and maybe some cream was vibrating to the top of the concrete in the grout box right in front of the paving machine. But they also observed that on the same day when they paved the control section, so it may have just been, particularly how they had the mix dialed in on that particular day of paving. So some of the testing that the team did at the time, they monitored calorimetry, and you see two sets of two different curves here. They also, during the same year, the team did a sister project that was where they used lightweight fine aggregate on a full-depth conventional concrete pavement, so they were able to look at both the internal curing of both an overlay and a conventional concrete pavement on another county highway. The dashed lines indicate the internal curing sections. The solid lines are the control sections. So you can see calorimetry is indicating enhanced hydration through the first several days after placement for both the overlay and the conventional section. The difference here between the dashed line is a little bit greater for the overlay, so potentially indicating that there was maybe a little bit of enhanced benefit there for the concrete overlay section. They did testing of various mechanical properties, casting samples on site. So what we see listed here on the left, we have compressive strength. So again, the dashed lines indicating the internal curing sections and that they both achieved higher compressive strengths. And again, we actually see the benefit looks like it's greater in the concrete overlay here, at least relative to this other project that was done. I believe that was an 8-inch thick concrete pavement. Same story, the plot on the right there is surface resistivity, so testing cylinders to infer permeability, long-term durability. Again, the internal curing sections were able to achieve greater surface resistivity values. And then finally they did take some samples, look at them under the scanning electron microscope, and noticed that it appeared that there were fewer unreacted cement particles still remaining. They did tests at 7 days, 28 days, and 90 days, and at each step in the process, it looks like the sections with the lightweight fine aggregate were all able to achieve greater amounts of hydration than sections without. So in general, a lot of kind of these benefits or properties of using lightweight fine aggregate that we've seen cited, we've seen evidence of in these sections here when we look at them compared to the control. And then finally, the last one that's pretty interesting here, the team did LiDAR testing to look at the shape of these concrete slabs out in the field for I think about a year after they were initially constructed. And what they found was that the internal curing test section appeared to demonstrate a reduced moisture gradient, both initially after construction and when they visited spring and summer and fall and winter over the following year. And the gradients that they measured through instrumenting the slab appeared to be less in the internal curing test sections. And with the LiDAR measurements, they also noticed that did in fact correspond to less overall shape change in the slab. So it appeared to have a not as much of a built-in curling or warping profile, and then it didn't experience as much movement between measurements when they went out at different times of year and different times of day relative to that of the control section. So obviously this scatter plot here is just showing the gradient versus the movement that they measured through LiDAR, but it's probably easier to look at this from a visual. And these are kind of the results. The picture on the left there is the LiDAR scan at one particular visit. It looks like it was in the winter in the morning where they looked at this section. And you could see an overall flatter profile there for the internal cure section relative to the conventional section. This is interesting to look at because most pavements, their kind of built-in gradient is a curled up shape. And these projects, I was reviewing the report and looking at the measurements they took at different times of year. It appears the default control section here actually did have a built-in curled down shape, and it was mostly curled down, which is interesting. We've seen projects like this before. It's just not the typical behavior for concrete pavement slabs. But again, the internal curing, did not have as much of a gradient as the control section, and so it generally had a flatter profile. And you would expect in the future that it would also then be a smoother pavement. That's where we can start connecting the benefits of internal curing to global warming potential. So putting everything together here, if we are able to realize some of the benefits of internal curing, such as reduced warping, which, again, can reduce the stresses that we experience in the pavement slab under traffic and increase the smoothness of the pavement, that can have a number of benefits to the overall life cycle emissions associated with the pavement. Again, just longer lasting, more durable, less future maintenance, but also, again, reducing fuel usage during the use stage of the life cycle assessment from the vehicles traveling on the pavement, because we have a smoother surface potentially that we don't have to expend as much energy to travel over the pavement. And, some of the other things that we're hoping to design for durability, could also involve using less binder in the concrete, and that kind of plays in pretty well with the benefits of internal curing. And then again, some of the other things that we're looking to achieve with concrete overlays, if we're able to reduce warping, maybe that allows us to optimize our concrete overlay designs to some extent, and maybe that would be something that would allow us to potentially reduce the thickness of our overlay design. And then again, the other benefits that we're looking to achieve with concrete overlays in the first place, those can certainly help play into global warming potential. Again, relative to new construction or a thicker, full-depth conventional concrete pavement slab, we don't have to use as much material in our concrete overlays. Looking very long-term, or particularly going back to the original construction, we're utilizing the existing equity and trying to keep an existing roadway that's already been constructed, in good condition and improving in current condition. And just again, anything you do to extend life, help ensure a longer-lasting pavement is good over the life cycle. And again, kind of a lot of different design goals that we're looking to achieve, sometimes for different reasons. Can end up being they can come together and end up working together pretty well in these types of contexts. And again, critical part about this is, we're not just taking something out of the pavement when we do this, or we're not compromising performance. We're able to achieve these objectives while hopefully enhancing performance. And I think we've seen, based on the test sections that were built in Iowa several years ago, we've seen, quite a bit of evidence that we were able to enhance the performance of those concrete overlay sections. So in conclusion, internal curing does appear to be a good sustainable solution, not just for, buildings, bridge decks, but also for our concrete pavement infrastructure. And overlays does appear to be a particularly good use case, given, again, it's a thinner pavement element. It might be more susceptible to curing related issues, and so internal curing could be particularly helpful there. And, again, supports reduction in carbon emissions while also improving the quality of the system. So that is all I have for this morning, and I guess we'll wait till then for questions. So I'll stick around.